Should you be scared of Unix signals? No. Well, maybe a little. Basically, Unix signals are a way for the operating system to communicate with your process when it's running. This allows you to catch signals that are very important that the operating system is telling your application that some things are happening, such as I'm going to turn you off because you failed to follow my rules, or I need to pause you for a moment because of XYZ reasons. One of the best reasons is when your application is being terminated due to it needing to be turned off. Usually in an auto-scaling environment like Kubernetes, you can receive a Unix signal that says shutdown imminent that allows you to do a little bit of extra work, like some cleanup, closing some things over here, writing a little bit of data to the logs, and then you can move forward and your application can exit gracefully. Julia Evans talks about using Unix signals here, and what is the Unix signal? Essentially, it's a way, right, for you to catch some interrupt from the operating system and run some function. You can tie it into a function, right? A callback. So for example, you can catch any sort of signal. There's a lot of different kinds of signals. The ones that you wanna catch are the ones like the interrupts, right? Where they're saying, hey, there's something that you can ping from the OS that allows you to maybe rotate a log file. All right, Julia walks us through here an example. What you could do is leveraging Linux kernel API calls, we can register a signal like SIGALRM to one of our functions. And when that signal is sent to your application, basically it allows you to run a function. For example, here Linux kernel says, hey, it's a signal, which then might stop your process. It saves all the registers in your process and then it runs this function, which means that all the other code that was currently executing pauses, and then it jumps immediately to your awesome function. And then once that awesome function is done, it puts everything back and sends you on your way. However, like any tool, caution is required. Timing is crucial. For example, in this case, we need to be careful because other kinds of signals can cause the same thing to happen, right? It can pause everything and then jump to the next function and then pause that and then jump to the next function, and then we've got some problems, right? Because we don't want to have to continuously be in this scenario. So we have to be careful about what we're doing. So for example, if we're doing a read or write system call and there's a signal, your read will be interrupted. Oh, that seems like a problem, right? Because then it has to process the next signal and then it just keeps pausing everything, bringing up a problem. So we do need to be careful. Is there a way around it? Let's find out. Okay, well, it seems like there's even more of a challenge because if you rely on any complex data structures where you have multiple applications or threads accessing the same memory structure, that advanced data structure, and you have locks involved, you could be in a situation where the lock gets set, but then in the case of where you're interrupting with the signal and your function handler could no longer access whatever data is in that advanced structure. That seems like a problem to me. Okay, we see here that Jesse points us out that if we run man 7 signal, we have a list of functions that are safe to call from signal handlers. So that's probably what we need to be doing, is we need to watch out for what kind of code that we're executing within our handled signal callback function. Actually, kind of curious. Let's pop that up right now and see what that looks like. All right, I popped open here the manual for signal, and we see what the function signature looks like, and it passes an integer value based on what kind of signal it is that we're handling. And I scroll down here, and we get a list of signals. Look at all those signals. There's so many. I didn't realize how many signals. There's only a few that we really deal with on a day-to-day basis, right? For example, SIGUP, SIGINT, and a couple of these. There's also, wow, look at all of these signals. Okay, and then there's some SIG users which can be defined. For example, if you're running Nginx, like Cloudflare, they will capture one of these signals to then do some maybe work extra on the disk for rotating logs, things like that. All right, now we have signal safety open up here, and then we can see that the set of functions follow here required to be async signal safe. So this following list appears to be the safe list that we can use when we are executing code within a signal. Interesting. Quite a few. Oh, really? Okay. Well, there's actually quite a lot that we can do. Okay, it even says we could read to. Interesting. Okay, well, what we need to do is just make sure to check to see if the functions that we're executing in any underlying code, say if we're in Python or Golang or Rust, whatever is being called underneath for the kernel APIs and different modules, we need to make sure that it is in this list when we are catching signals and processing them. One of my favorite use cases for catching signals is when we are writing serverless containers that run in sort of a microservices fashion inside of a Docker. And then what we can do is we can have our application code register for a signal listener to check to see if my application needs to be terminated due to changing locations, or maybe it's just a downscale event, right? We don't need so much hardware online. The number of pods running in the Kubernetes cluster, we don't need them anymore, so we're going to turn them off. What we need to do is catch those signals and then do a little bit of work so we can cleanly exit our application before it's terminated. We also see in this case, we also have an example here on the screen of Unicorn gracefully restarting with the SIGHUP, the SIG interrupt, which allows you to catch that, and it will allow a graceful restart. And another important one is SIGSEGV, which is a segfault, which, that's a problem, right? We don't want segfaults, but when they happen, they'll happen because your program went out and beyond with what it was supposed to do, so it got it's going to be terminated. What you can't really do a whole lot, but what you need to do is make sure that you can output any final data, so that way the stack trace, when you go to debug the core file, will be a little bit more useful. There's also another approach if you want to avoid some of those shortcomings of using the standard signal interrupt. You can use a file descriptor and any sort of epoll, poll, or select, which allows you to capture those events and then come back to an event loop later, so that way you can fully process whatever that signal is without being interrupted. I like this approach. This approach sounds very satisfying. It does require a little bit more effort because you will have to register for listening on a file descriptor, so that way you can receive those events in a queue in an event loop, which is going to be a little bit extra work in this case. You probably don't need something like that for normal operations, but if you're going to be using signals a lot, then this is for you. This is what you'd want to use. All right, now that we went over Unix signals and how they can be very useful to our application, we realized that we don't have to be afraid. We just can be careful. Here, Julia describes to us that our fears and uncertainties about things can't be based in fact. And guess what? It's absolutely worthwhile for us to jump in and use Unix signals as we operate our microservices and other application use cases, because it allows us to do extra work when we need to do graceful restarts, graceful shutdowns, and things like that. These are very necessary when you're operating systems in production. They should have signal handlers.